Okay, so in this video, we're gonna look at more of the overview of hypothesis testing and look at all of the steps, but we're not gonna actually like do a full hypothesis test yet in section 9.1. So turn to the page that says process of hypothesis testing. So the first thing is we're gonna state the claim, and we already did this. We're gonna write the null and alternative hypothesis. So that's always step one, which we just learned. For the null hypothesis, so this, we always assume it's true. So we always assume the null hypothesis is true. So remember, I said it was like a court of law. So it's like we always in a court of law assume someone's guilty and someone's innocent until proven guilty. This was the same thing. We always assume the null hypothesis is true until proven false. Our goal is to determine the plausibility of the null hypothesis. So based on our sample evidence, does it show me enough evidence to say that we believe the null hypothesis is not true anymore? And that's what we're trying to determine. So then we collect and present evidence. So sample data is collected. So again, we're just going to be presented with the sample data. We're not doing the collection, but that would be technically the next step. So then we analyze the data. Right, so first thing they do is they find the test statistic. And the test statistic is either the z-score if we're using a normal model, which would be for proportions, or a t-score if we are using the student t model, which is for means. Okay. Then we calculate the probability of getting the results of the sample given the null is true. This probability is called the p-value. So what we do again is we have our model, either the normal or the t model, okay, and we put our null hypothesis value as the mean. Okay, so it'd be either mu naught, or if we're doing proportions, it would be p naught. Then we get our sample data, and so we calculate either p hat, our sample proportion, or x bar, our sample mean. And using that, okay, we calculate either the z-score or the t-score. So if we're doing proportions, we do the z-score, and we would do like p hat minus p naught over, and then our standard deviation for it, I'm gonna just write sigma p hat. Okay, and we would use again our normal formula, which is that square root, and we would use p naught because that's what we have over 1 minus p naught over n. Okay, we're not going to do this by hand ever, but this is the whole idea. So we find that z-score, and again, we would change this to a standard normal model. So this would become, the mean would become 0, and z would fall on one of these sides. And then we're going to calculate the probability. So if it was a right-tailed test, we would calculate the probability that it's greater than it. And this probability, or this area here, is called the p-value. And if we were doing means, it would be the same thing, the sample mean. So if we had, again, our null, mu equals mu naught, if my alternative would be mu is less than, so it's a left-tailed, we would calculate the t-score by doing x bar minus mu naught over, and again, I'm just going to call it the standard deviation of x bar. We won't really worry about the formula for it. And we would calculate that t-score. We would look at, okay, this is the mean being 0 for the standard normal, and then t would come over here because it's a left-tailed, so it would be less than that value, and we would calculate the probability in this left tail. And again, that area or that probability is called the p-value. Okay, so the p-value is the probability of getting the results of the sample. So getting the sample mean or the sample proportion, given that the null is true, okay? So we always base it on the null value. We create our model around the null value, and then we find where is my sample mean located. And based on that, we determine this p-value. And again, that's the probability of getting the results of the sample given the null is true. So we will have a lot of different types of models, but one model, if we're doing proportions, is called a one proportion z-test. Okay, think one proportion z-int that we did for confidence intervals, but we do a test, which is a hypothesis test instead of a confidence interval. We can use the normal model. To help calculate the p-value, which is kind of what I showed here. But for this class, we'll use technology to find the p-value. So one way would be to do it is to like draw your normal curve, find your z-score, and then use the normal CDF command to calculate the probability. But there is also just a command in our calculator that will do that all for us, and that's what we will use in this class. So then we state the conclusion. So we determine whether there is enough evidence to support the alternative hypothesis. Very similar, again, to a court of law. Do we have enough evidence to say that this person is guilty? Now, the whole idea is if the p-value is small, it indicates the results are more likely not due to chance or sampling variability. Okay, so we've already talked about every sample is slightly different, and so it's sampling variability. And so it makes sense if we have a normal model and I have my population mean that X bar is somewhere like slightly off. That's not alarming. That's probably due to sampling variability. But if I do my sample and X bar is like all the way over here, right? And the probability of getting that X bar, assuming that the null is true, is very tiny, that indicates that it's most likely not due to chance. It indicates that this null value is probably not true. And so if my sample mean is a lot larger than my null value, or again, a lot smaller than my null value, and then that probability is really, really small, it gives us evidence to believe that this population mean that we thought it was is not right. Okay? So this is called, we don't believe it's true, and this is called rejecting the null. Or rejecting the null hypothesis. Okay, and when we reject the null, we're saying, okay, we don't believe this null value is really true anymore, and we think there is evidence that the alternative is true. If the p-value is larger, which if the p-value is larger, that means that the sample mean is going to be close to the population mean. So this is a much larger area, so this p-value is going to be larger than like this one over here. So if the p-value is larger, then the sample data does not contradict the null hypothesis. It's probably just due to sampling variability. And this is called failing to reject. The null. And then we say, because we're not rejecting this, that there's not enough evidence for the alternative hypothesis. Okay. So again, I understand that this might be really confusing and not make a ton of sense right now. We'll again be doing a ton of practice problems and I'll keep explaining it. So hopefully it will start to make a little bit more sense of what we're doing as we go. So the whole idea is we find that p-value and a smaller p-value supports that the null is false. And small enough p-value is determined by it's called significance level. Which we call alpha. Okay. All right, and again, I'm really bad at drawing these. I tried to draw these in class the other day, but this is alpha. It's like the Greek letter alpha. That's how it's right here. That is called the significance level. So the whole idea is when we find this p-value, like here or here, what is considered small enough that we don't think it's no longer by chance. Instead, we think that the null is wrong. And so we have to have a cutoff for what is small enough. And the cutoff is called the significance level. And generally the significance level is determined before researchers collect the data. Like when they're usually writing their null and alternative, they'll say, I want a significance level of 5%. So I want just a 5% chance of making an error. And alpha is the level of significance or the chance of making it's called a type 1 error. We're going to learn more about type 1 errors actually in the next video. But the whole idea, once I explain what type 1 error is researchers want the type 1 errors to be small. And so we set a significance level for the type 1 error to be small. So recall, we use a rule of thumb that probabilities less than 5% are unusual. So a typical significance level is 5%. If our probability is less, if our p-value is less than 5%, that's an unusual probability. And so usually we say that's enough to reject the null hypothesis. But the value may change based on the field of study. So in hypothesis testing, the value is set at the beginning of the testing process. It's either a 10% significance level, which is 0.10, a 5%, or a 1%. Those are the most typical ones that you see. And again, it depends what type of research they want. If it's a big deal that we make an error, like it's gonna drastically change the field, they might make the significance level like 1% because they don't want any possibility of an error. If it's something like that really doesn't matter, they might make it like a 10% significance level, that if we made a change, it wouldn't be a ton of money or time. And so it's okay if it's a 10% significance level. So we are going to use, it's called the p-value approach. There's two, it's like the p-value approach, or you can also do it based on their critical value, but we always do the p-value approach in this class. So for the p-value approach, we calculate that p-value, that probability. And if the p-value is less than or equal to the significance level alpha, we reject the null hypothesis and we say the results are statistically significant at that alpha level. If the p-value is greater than alpha, we fail to reject the null hypothesis. Okay. And so when we fail to reject the null hypothesis, we say there is not evidence for the alternative. When we reject the null hypothesis, we say there is evidence that the alternative is true. So this is what I was just saying. So there's two conclusions from hypothesis testing. If we reject the null hypothesis, which again means that the p-value is less than or equal to alpha, this sample data indicates that the null is false, and we're concluding that there is evidence for the alternative. If we fail to reject the null hypothesis, then we're not rejecting the null. Okay, we still believe the null is true. But just like a court of law, we never say like this data proved that the null is true. we're just saying that this sample data is not enough evidence to say that it's false. So one sample can't prove the null true, it can just prove the null false. But it can say that this sample data does not support that the null is false. Right, and so we're leaning toward the null being true, but the sample never proves the null is true. Just like again, in a court of law, we never say a person is proven innocent, the claim is always that they are not guilty. Okay, so there is not enough evidence for the alternative hypothesis. We don't know the null is true, but there's just not enough evidence to reject it. And notice that the decision for hypothesis test reference the null hypothesis, H naught, while the conclusion always references the alternative hypothesis, H1, within the context of the situation. And we're gonna write a ton of conclusions, and this is gonna be key when we write conclusions. Okay, so that's the main overview of hypothesis testing. And then I'm gonna make one more video on the types of errors.